Good afternoon, everyone. I'm happy to see 30 odd people here. I was expecting 30 less. So thanks for staying on for day 4, 2 p.m. I know you guys want to go home, so we'll make it fast. Are you guys tired of hearing the word AI yet, or you want to hear more? Nobody? Okay. So anyway, I'm Gautam. I support the product quality engineering team at Meta. Primarily, our team is responsible for taking hardware from concept to mass production phase. We are responsible for defining manufacturing and test processes as we go along the process. Soumya is my colleague, and we'll be covering the testing of AI systems as to what is different about AI systems and why is it necessary, what's important. So the agenda is, we'll talk about some of the background and challenges of testing AI hardware, what's the methodology and key metrics that we are tracking, some of the experimental results that we've run through and we'll share with you guys, and finally the conclusion and what's the future look like. Why is it important? So there's the technical reason, but I'll tell you what my personal reason for this is. I don't want calls on weekends saying that this data center is down. So I don't want that, right? So we don't want getting calls on SEVs or any kind of system events which take down hardware clusters. So that's my primary reason. Second reason, of course, the technical reasons are out there. So we have to not just test it like traditional systems, but also look at it from a workload perspective, make sure the entire workload and the rack works as a system versus how it was in the traditional hardware space. So traditional versus AI system testing. To explain traditional systems, let's say we can take an example of a vanilla ice cream. It's just basic 3 ingredients. It's vanilla, bean, sugar, milk. It's very predictable. It tastes the same. You can go store to store. It's probably going to taste the same. Versus AI system is more heterogeneous. There's a lot of components like GPUs, CPUs, ASICs, accelerators, memory, and they all have to work together in tandem. There's a connectivity piece, which is also very important. And then there's the software-hardware co-validation, which is extremely important when it comes to AI systems. Anomalies usually go undetected when it comes to AI systems if we use traditional methods of testing. So I'm going to skip the slide. I'll come back to it. So just give you an overview of what we're referring to when we talk about different levels. So there's the server level, which is the basic building blocks of the server. And then you have the rack level, which is servers integrated into a rack. And then multi-rack setup is something which AI systems operate in as a cluster in the data centers. So coming back, what are we going to do from a testing perspective, which is different? Of course, we have to test the functional blocks which build the server. So that's the component level testing. Then once it's integrated into a rack, we have to test it at a rack level. And then finally, we have to test it as a solution, which is deployed in the data centers. So that's where you have the multi-rack level testing. So also what is important here is we have to build in a continuous monitoring and a feedback loop system, which kind of gives us information as we test, and we can dynamically optimize test. This is the basic workflow of how we've been covering test across different levels. Of course, the first level is the basic functional block, which is at the server level. And then when it comes to the rack level, we have a full firmware, software, and hardware validation cycle looking at connectivity checks and the functionality. And then when it comes to multi-rack cluster testing, we do have performance benchmarks, back-end, front-end NICs, and the entire system to work as one for supporting AI workload. Soumya will go into the details of how we test and what results we've collected and what the future looks like. If you're interested, there's also a paper we've published in IEEE IMAPS, which you can go refer to. Thanks, Soumya. the greens for the next slide.
Thanks, Gautam. And thanks for giving the good context. Just to remind you again, this is manufacturing, and this is not validation testing. The whole context is manufacturing testing, which is much more challenging, where we can't put a scope there, we can't put PCI analyzers there, and we can't do a lot of things that we can do in data center testing. So we have worked around all these challenges, and Gautam gave context of how different it is from traditional ways of testing. So let's deep dive into seeing what test methodology we are proposing, keeping in mind the factors like scalability, accuracy, and performance and repeatability. These are the key words when we are manufacturing at scale and deploying it to data centers. The data we have is from what we have seen and experienced. So I can't see the slide. OK. So what we are proposing is more of a hierarchical approach. So because you want to weed out all the faulty parts or the faulty bottlenecks, or the bottlenecks that we can identify as early as in manufacturing before deploying these systems, AI systems, into data centers. And we first go into component level. Component level in a traditional hardware server system is going to be just looking at hardware functionality evaluations. But whereas when we look at AI systems, it's a little more than that, more than just hardware functionality. You want to make sure this AI component works as expected in the real use case, and that means non-deterministic behavior. We are looking at validating at-scale non-deterministic behavior components. That gives you same inputs, but every time it could be a different output. And this accuracy and predictability is what makes these AI systems very challenging to evaluate in manufacturing. And we recommend what we propose in our plan or in the recommended test plan for manufacturing is first look at the component level. It could be ASICs, it could be accelerators or training ASICs or GPUs or any other AI components that is in the systems. So run like basic, what we recommend is beyond hardware evaluation, functional testing is run actual synthetic and real workloads as close to as we can in the data centers. For example, run GemBench, right? But run GemBench for different input data types, and it will evaluate how the ASIC behaves. And similarly, run models like Llama and run them on the single GPU or a single ASIC and evaluate how the performance look like, how the accuracy look like over time, as much as we can in manufacturing. The key thing when you're testing an AI component is also how you analyze the data. It's not going to be X and Y metric that you look at in the standard systems. You want to compare what the GPU to GPU variations are. We have some data to show how it impacts in the data center later in the slides, but that's what you want to do a statistic. What we recommend is implementing statistical ways of analyzing the data at the component level and screen out these GPU or ASIC parts ahead of time in manufacturing. And based on our experience, we have some data to share in the upcoming slides, but you want to look at the metrics like accuracy and error rate and identify at the component level, AI component level, before you go into further hardware integration. And going to next level of hardware integration is, how do I go? Is server integration.
Oh,
yeah. Now we have weeded out any of the AI component itself. But now the working GPUs or working ASICs have made it to the next level of testing in manufacturing, and they are servers in our next hardware level integration, right? But here, the focus areas are slightly going to be different. Yes, the accuracy still holds good, repeatability still holds good, performance metrics still holds good at component level. But beyond that, we also propose you need to evaluate the subsystems of GPUs and subsystems of ASICs to ensure the functionality of the AI system as a whole. And that includes, where you run again, we would highly recommend beyond hardware validation to have a reliability factor into account. You want to look at the subsystem communication. For example, if you have GPU to GPU communication, ASIC to ASIC, and GPU to CPU communication. And this you can do only by running also synthetic or the real workloads in handy. Otherwise, there is no way you can evaluate the AI systems and guarantee it's working in the data centers. So we do have data how we have run this, and where here you look at distributed models between the GPUs or ASICs, and you also look at concurrency. And when you run concurrency, some of the metrics you're going to look at or issues that you're going to find are related to temperature, memory utilization, and so on. So these are, and when you do memory utilization is a bottleneck, you can give feedback to the design very early on in the cycle, and this is not validation, right? At the manufacturing, you can, when you're manufacturing at scale, you still can identify bottlenecks and give feedback to design teams. Some of the KPIs here, again, are very critical. Look at them at statistical analysis and not individual components or individual servers. And the next level, again, of hardware integration in manufacture is going to be validated at component level, at server level, and the next level is going to be the rack integration. And rack integration is a different beast altogether. Just imagine we are doing at scale. It's not at the lab setup, and it's not where you're running stress over 20 hours to see if this part breaks. We have hundreds of racks in assembly, and we want to ensure as much as we can it works as expected for an AI workload and not just as a hardware rack. So that's the challenge that we time and again face in manufacturing, but looks like based on our experience and results, we have found somewhat a very good solution where we have end-to-end solution where we do run models like Llama and look at the results. And again here, the communication between, this is at scale, right? So, and you want to look at the communication between the servers, how do they communicate, and how do any GPU in the rack or any ASIC in the rack should be able to talk to another ASIC. So these are the workloads we have designed to evaluate thermal and network limitation and identified some of the performance issues as well very early on before deploying them into data centers. And power and thermal have been the most, and network has been the most focused areas when we test the rack level and identify the issues very early on. And moving on, all this is fancy when we put it on paper, but have this contributed, this hierarchical methods, have they contributed to identifying issues? Yes, they have. And we have found, and in some cases where we have seen 85% failure rate in the beginning, but the screening out in the after deployment. But when we have implemented this hierarchical test methodology, we have cut down our error rate to much less than 5 to 10%, and then less than 2% before shipping with this test methodology. It's, of course, in works, but yes. And want to share some of the experimental results. Gautam, can we go back the previous slide? This is, I want to share one of these we wanted to share. This shows what we did was we ran synthetic workloads for different input data types and analyzed the results. We found there was GPU to GPU variations, but based on our, it all passed the test, met the criteria of what we call performance pass, but is it still ready to be deployed? Quite not yet, because when we compared the results. There was variation in some cases. If you take to the least to the highest, the distribution had 9% variation between the GPUs. And how does this impact? Because all these GPUs, ASICs have to work together in cluster level setup in the data centers. These 9% variation, while functionality, they all work well, but when you translate it to accuracy and efficiency, they do not translate very well. So this is when I said when we have to look at statistical ways. You can't individually set a performance metric to a given component or a given subsystem and say this works. But what are the variation between the parts when you run them in distributed mode or concurrent mode? Is the efficiency going to be impacted? So functionality-wise, so far, we have noticed that it stuck well behind the data we have, well behind, under 10%. And so we didn't have impact. We haven't seen the impact on the functionality itself. But with this, we have seen the efficiency impact, because you're processing, one component is processing the workload, it will have to wait for the latency, it will have to wait for this second component to process if it's 9% slower. So that's what we wanted to highlight. So we are implementing this in manufacturing to catch such efficiency issues early on. And another thing is when you in the past, when we identified when we ran validation in manufacturing or testing in manufacturing as a traditional way of running for just functional testing, we did not identify such issues. But when we ran workloads like GEM, very low level GEM for different input types, and also Llama, we were able to detect some of the strange behaviors that were exhibited, like frequency dips when we run concurrent workloads. And when we ran, this plot shows just that. And when we ran the distributed loads, the thermal efficiency was affected. So these are the things that we did not catch earlier, hence the proposal of running Llama and GEM and for unpredictable behavior very early on in the manufacturing cycle. And at the rack level, so the rack level was very interesting. We did run collective networks at the rack level to test the communication between the servers, and it worked fine. But when we ran specific targeted collectives, the communication between the two random GPUs or two random ASICs, we did find that while the results set past metrics, the accuracy took a hit. And that could only be done while running such targeted tests at the rack level, where you have to check the communication between the parts. Many links and many data paths are involved, but we have to formulate the test at the rack level to evaluate the communications and run also the collective, some kind of collective networks or Llama synthetic workload to identify such accuracy issues, which do not show as black and white when you do traditional hardware testing. So this is one of our issues that we identified and worked to resolving. So that, the benefits of our proposed test methodology, as we shared the results, are quite obvious. So the issues that we shared were not identified with the traditional approach. And with our approach, it's a holistic solution where we test the end-to-end while running synthetic workloads, keeping in mind cluster level setup and rack level thermal issues and memory bandwidth, and providing feedbacks to the design teams. And establishing it is part of our proposed test methodologies, establishing a feedback loop, monitoring loop with the software teams and with the design teams. While it's manufacturing, if we identify bottlenecks while running these tests, very early on before deploying these systems, we have continuously established a feedback loop of providing what the bottlenecks are, where we see the issues. It might be thermal, it might be memory bandwidth utilization, or PCIe bandwidth. Any of these bottlenecks have been identified, and that feedback loop is part of a proposed methodology, which helps improve the yield in manufacturing and at the same time provide feedback to the design teams as well. And this is just a flow chart showing why it's more pictorial way of showing hierarchical test methodology and eliminating issues component level very early on and before we test the rack, and rack level before we test the cluster. So this is just a flow chart to have a visual. That being shared, it has worked. Yield is improved. We have given feedback to improve, and we have identified the KPIs that are critical to test the AI systems and analyze non-deterministic behaviors very early on in manufacturing. At the same time, there are future steps we would like to take, improve methods of analyzing in the manufacturing, make it more efficient, make it more scalable, and come up with new statistical ways, and improve test coverage as well. We tested right now with Llama and few GemBench with varied inputs and data types, but improve test coverage with additional, which are close to real world traffic is work in progress as well. So here are some of the references we have listed, and feel free to reach out to us with any questions, and yeah, papers are listed there with further evaluation and your reference. And thank you. I'd be happy to take questions or any discussions you would like to have.
Yeah, thanks for the presentation. So when you're running the real world or your workloads, how long do you have to run before you actually catch the issues?
That's a very good question. I'll take it.
Yeah, go ahead.
It's a very good question, because that is one of the challenging part. This is, remember, to remind you, it's manufacturing environment. It's not a validation. So that is something we, again, when we said feedback loop, that's part of feedback loop as well. So we very early on, we based on the validation results from validation team and hardware evaluation, we do come up with the optimized, there's some educated guess on, and based on the previous product, we do come up with the test times. But that's an ongoing feedback loop. We focus more on where we start seeing the issues. For example, if memory is an issue or the memory utilization is an issue, we improve as the different cycles of manufacturing we go through, and we keep fine-tuning the test times. But it's a right nail that you hit there, in the sense we don't have the luxury of running it hours. But we do run the stress test to 2 to 4 hours, and sometimes early up to 12 hours at scale. Okay. But as we go into mass production of thousands of racks, these are going to be fine-tuned based on the issues we see.
Yeah. I mean, beyond a certain point, it's diminishing returns on test. So we constantly try to optimize for scale, especially in the mass production phase. Cool. All right. If anyone's interested in this topic, you know where to find us. We're happy to collaborate on this further. This journey's just started for us. Thank you.
Thanks, everyone.